So this is the multicollinearity video tutorial, and we're going to look at perfect and imperfect multicollinearity. Um, and first we're going to demonstrate it, and then we're going to look at how to detect it, and then we're going to talk about kind of what to do if you encounter it, say for example in your project. So let's create data that exhibits perfect multicollinearity. Or I guess technically it's perfect collinearity because there's only two variables, but whatever. So first we're going to create x1. We're going to say x1 run if 25 0 100. So this is going to grab like 25 random deviates from the uniform distribution from 0 to 100. So that's great. And then x2 is going to go ahead and it's going to be 0.25 times 0.25 whatever times whatever our x1s are that we just created. And then you can look at the correlation between these two, and it's going to be perfectly correlated, right? Because we just created it as such. So now if we create some y data and then run a regression model on it, you can see what R does when you try to include perfectly correlated variables in a regression. So let's create the y data. So y is going to be 0.5. This is kind of some arbitrary data we're creating here. So 0.5 times x1 plus 0.5 times x2 plus a random normal like error. So this is going to be our error, r norm 25, whatever. Great, and then our model is going to be a regression of those x's on the y, so it's going to be lm y on the left side tilde or squiggly x1 plus x2. And then now if you look at the summary of the model, you're going to see that R says, okay, coefficients 1 not defined because of singularities, and it kicks out x2, it says NA. So this is what R is going to do if you give it perfectly correlated explanatory variables. And then let's go ahead and include too many dummy variables and look at what happens there. So let's create a dummy variable, male. And we're going to create it by sampling from the set of numbers 1 and 0. So you do that by putting a C and saying 1 comma 0. So that's telling R like concatenate or combine these two values and then choose from them 25 times and replace so that you can get a 1 or a 0 more than once, which is helpful because we need 25 of them. And if you want to learn more about how these things work, you can just type in like question mark sample and then open and close paren, or you can type in or you can Google like sample function R in Google, and you can learn all about these things. Whatever. So we're creating this data. So male. So we have our data here, and then we're going to create female. In this example, we're embracing like this gender binary. So anyway, that's what we're doing for this data. And then look at the female. Okay, so if you're not female, then you know, you're male here. And then we're going to create some y data again, and then run a regression and see what R does. So y is going to be like our old old friend x1 plus male plus 0 times female plus R norm 25. Great, and then we're going to regress y on x1 male and female. So oops, too many parentheses here. So y on the left side, and then x1 plus male plus female, and then look at the summary of this model. And then again, R is going to kick out one of the dummy variables. So then you can correct this by dropping one of the variables. So you say, okay, our new model is going to be model. It's going to be lm y and then tilde x1 plus male. And then when you look at the summary of this model, you're going to have not that problem. So that's great. And what's much more common is imperfect collinearity. So let's bring in U.S. macroeconomic data and look at this. So our data is going to be called US DAT, and it's going to be a CSV file, of course. So it's going to be read.csv, and I'm going to pull it in from the internet. So http:// I typed this wrong. HTTP would be helpful. /content.csbs.utah.edu/fouls/econ 4650/data with capital D /original. Sorry, I'm trying to read and write at the same time. It's apparently I haven't mastered that yet. Original Longley dot CSV in quotation marks, and then comma, and then header equal to true, capital T. And let's look at that. So this is like macroeconomic data. You've got things like gross national product, unemployment, total employment, year, armed forces. Looks like that must be armed forces spending, population, things like this. Great. So the first thing we're going to do is we're going to look at measuring collinearity by looking at pairwise correlation coefficients. All that means is you find the correlation between any two variables. We can have R find the correlation between all the variables in pairs quite quickly by typing in COR and then US DAT, and then there it is, right? So you've got obviously you have some fairly high correlation coefficients here mixed in, so this is going to give you a heads up that you're going to be looking at some collinearity issues, right? Like looking at, for example, total employment and GNP, or population and total employment, right? These are like extremely high correlation coefficients. And let's plot one of these so you can see what the imperfectly correlated data is going to look like. So if we attach our data set and then we say plot, let's do population and GNP, and the title of the plot is like US pop and GNP 1947 to 1962 or something like this, right? And then it's going to be like some huge graph. So we'll pull that down, move it over here, and we'll throw in like a regression line there. So AB line, LM, GNP, pop, and then color equal to red. So this is kind of cool because let's say you're working on your final project and you want to demonstrate or show, like as you're investigating if your data has multicollinearity and you're investigating the relationships between the variables, this is a good way to do it. You can look at the pairwise correlation here, and then you can plot it and say, okay, I've plotted this, like it looks like there's a really strong relationship here, danger. I mean, so your project is not so much about like whether or not you can find data without this kind of problem, but it's more about like what do you do about it, right? So that's what we're going to kind of talk about next. It's not as probably a solid answer as you might want, but that's kind of the nature of econometrics. So now let's get to the heart of the model, right? So, or the heart of the issue. So basically, the precision of the estimator is affected by the correlation between explanatory variables, right? So you can have more variance, which can cause like unexpected signs and things like that to happen, and it can really mess with like it can reduce your t-score and things like that, or sorry, it can Yeah, reduce it. Okay, so let's look at what happens if you well, basically we're going to try and illustrate this with our data. So we're going to say GNP-OLS1 is going to be a linear regression of GNP on like everything else. So put a period there, and then a comma, and then data equal to US stats. Okay, and then look at this. So look at total employment. So it has a negative estimate sign in relation to GNP, which is not what we would expect, and it is not significant. Now, let's note what happens when we run like a subset model. So we drop some of these other variables. So we'll say GNP OLS2 LM, see GNP squiggly, and then totemp plus year plus pop. Tell it where to get the data. So now total employment has a positive estimate, which is probably what we would expect, and is significant. So this is like an example of sensitivity analysis. So if you pick a variable which you're worried about, or which you think is like important to the model, and then you play with what the variable, or what happens to the variable in terms of its significance and its standard error and things, when you choose different model specifications. So that's like an important thing to do. So if you have, let's say if you suspect you have multicollinearity, you can perform this kind of sensitivity analysis and say, okay, I'm going to pick out a few variables that are important, and I'm going to run a bunch of different regressions with them thoughtfully and try and see how they interact with the other variables and how it affects the model. Okay. So if you encounter multicollinearity, that's something that you could do. And basically the fundamental issue here is that if you don't know what the quote-unquote correct model is, then your inference is going to be kind of shaky when you have collinear data. So you have to perform this kind of sensitivity analysis of saying this is how this variable stands up in models with different variables which are also relevant. So anyway, now we can look at the variance inflation factor. So this is kind of explaining the book, but basically to calculate a VIF, you regress each explanatory variable in a model on every other explanatory variable in the model. And then if you get a VIF score greater than 5, then you might have a problem with multicollinearity. So again, this is something that would be cool to do, like if you're on your project and you're saying, okay, like I'm looking to see if I have multicollinearity. And it's in the car package, so you're going to want to install the car package, and then once you've got it installed, you can do library car. If you don't remember how to install a package, you type in install.packages, and then a parenthesis, quotation mark, name of the package, in quote, close parenthesis. Anyway, I think there's a tutorial on it on YouTube. I'm sure you could look that up. But anyway, once you've got it installed, you can say library car, and then run a VIF on, let's do it on our first regression, so GNP-OLS1. And here you can see our VIF scores are like extremely high, so we're definitely looking at issues with multicollinearity. Definitely larger than 5. I mean, some of these. Okay, I'll just reiterate what's in the text guide. There's no clear solution to the problem of multicollinearity. One approach is to become aware of it and do nothing. Sensitivity analysis is always a good path. Basically, you highlight variables of interest or focused variables which would always be included, and then see if regressions on sets of other variables which are excluded or included have significant differences in the estimates of the focus variables. And then that last bit in the text guide is an exercise in a Bayesian information criterion, and I'll leave that as an exercise to the reader. You can investigate that. That will not be on the midterm, but it's something that people do to select variables. and it's not. It is something you should not do. So, but anyway, thank you, and this is the end of the video tutorial.